So welcome to the last video of the course. Congratulations, we're almost done. This video is actually going to be a little bit lighter than the last few, mostly introducing you to some topics that get covered in later analysis classes and also numerical methods, engineering mathematics, and so on and so forth. So something we've been doing in the last couple of videos is writing power series. So that is, we have a function and we write it in terms of an infinite sum of some simple functions, right? So sum of aj times x to the j. Now, in linear algebra language, it sort of looks like you're writing the function f of x in the basis of functions 1, x squared, x cubed. Now, I should put a big warning here, right? This isn't quite right. We're not used to having bases of infinite spaces, infinite dimensional spaces like the collection of functions. It's not 100% clear how bases should really work. All right, but as a sort of vague heuristic, this is the idea, right? We're writing f of x as the sum of a bunch of other things with coefficients, okay? And that might lead you to ask, well, could we use another basis? That is, instead of using the monomials, could we use some other collection of functions and write something like, f of x is equal to sum j, aj of, something else, gj of x, where gj is some other nice collection of functions, not this one. And the answer, of course, is yes. In terms of the analysis we've been doing so far, there's nothing terribly special about these functions x to the j. All right, so we could do it, but why would we bother trying? What could we possibly get out of it? Well, I'm not going to give a comprehensive answer right now, but I'm going to give a heuristic which is going to justify what is probably the most common other basis. Remember, in linear algebra, there was sort of a natural basis, right? The one that looked like 1, 0, 0, 0, 1, 0, 0, 0, 1. That was what you sort of got started with when learning linear algebra. And then very often, when we would choose another basis, the basis would come by taking a linear operator or a matrix K and choosing a basis that diagonalized that linear operator. Now, in analysis, we can do the same thing. And in fact, it turns out that that's quite fruitful. Now, there's of course a natural follow-up question, which is, I know what linear operators are in linear algebra, right? They're just matrices. What are the operators that we work with in analysis? Well, there are quite a few of them, but the most important one is called the Laplacian, spelled like this. And it's just the second derivative operator. That is, the Laplacian applied to f is just d squared dx squared of f. And you can check for yourself that at least as long as you're restricting your attention to functions that have derivatives, this really is a linear operator on the collection of functions. Okay, so that's sort of a nice operator to deal with. And it turns out it's very easy to diagonalize that operator. That is, to find the eigenfunctions of that operator. They're exactly the cosines and the cosine, the sines and the cosines. Okay, so everything up until this point is sort of a heuristic. But what does the heuristic tell us? The heuristic is telling us, well, we can write f of x as an infinite sum of some other functions. And if we imagine what we did in linear algebra class, probably what we want to do is find functions that diagonalize some important operator. And I'm asserting to you that, in fact, one of the more important operators is the Laplacian, which is given by this formula. And then it's easy to check for yourself that the eigenfunctions of that operator are indeed the coses and the sines. That is, if you apply the Laplacian to a cos function, you end up with a cos times a constant. If you apply the Laplacian to a sine, you end up with a sine times a function. Okay, with all that heuristics out of the way, now we can get back to the careful math. It leads us to the following definition. For any continuous function f from the interval minus pi to pi to r, the Fourier coefficients associated with that function are given by these formulas here. So they're integrals of f with cosine functions, or the integrals of f times sine functions. And the associated Fourier series, or partial series, is given by this formula here. So it's the sum from j equals 1 to n of a bunch of coefficients times coses plus a bunch of coefficients times sines. Okay, so that's what we do. This is sort of the analog of a Taylor series where we're expanding in cos functions and sine functions instead of monomials like x squared, x cubed, and so forth. Okay. Now you're probably expecting the next thing that I'm going to do is talk about how Fn converges to f, right? So far when we're talking about power series, right, The natural thing that we did was we checked that often Fn converged to f pointwise, and then later on we proved in fact something stronger, that typically Fn converged to f uniformly. So you would hope, if we're doing something that's analogous to power series, that the same thing would be true. That is, the Fourier series would converge also to f pointwise. Unfortunately, life turns out to be not quite so nice. For a whole lot of pretty reasonable functions f, they have a Fourier coefficient, they have Fourier series, but somehow Fn doesn't quite converge to f pointwise. I'm not going to give an explicit example here because it's a little bit messy to do in a video, but it turns out that that's sort of a serious enough problem that we end up not talking very much about pointwise and uniform convergence when talking about Fourier series, or at least they're not quite as dominant as they've been for us in the last few videos. Instead, what you typically do is define an even weaker notion of convergence. So this is strong uniform convergence, pointwise convergence is sort of medium, and we define something else that's even weaker that's called L2 convergence, and we say that Fn converges to f in the L2 sense if this thing, the integral of Fn minus f squared, converges to 0. Okay? So you can see if you have pointwise convergence, or especially uniform convergence, you're going to get this as well. But this doesn't quite require pointwise convergence, right? You can have individual points where Fn minus f doesn't converge to 0, as long as this integral converges to 0. And it turns out that's sort of the right way to talk about convergence for Fourier series. All right, we're not going to do any more about that, but if you're interested, you're going to see much, much more of this in Math 3120. All right, with that small advertisement out of the way, we're done with the course. Thank you very much.